Now we start on the sorts themselves. The first one is insertion sort, the same motion you use when you sort a hand of playing cards. Insertion sort takes each element in turn and slides it left into its correct spot. The spot is somewhere in the part that is already sorted. It is exactly the playing card motion from the opening. Three ideas make it work. The prefix A from index 0 to index I minus 1 is always sorted. That is the invariant. We take A at index I, the next card, and shift every larger value in the prefix one step to the right. Then we drop the card into the hole once nothing bigger stands in front of it. We shift only elements that are strictly greater than the key. That is what makes insertion sort stable. An equal element never gets shifted past, so two equal keys keep their original order. Let's read insertion sort in pseudocode. The outer loop runs I from 1 up to n-1. We save A at index I in a variable called key. We set J to I-1, so J points at the last card in the sorted prefix. The while loop runs while J is at least 0 and A at index J is greater than the key. Inside it, we copy A at index J one step to the right into A at index J plus 1, and then we decrease J by 1. When the loop stops, we drop the key into A at index J plus 1, the hole we just opened. One small detail matters. We compare with greater than, not greater than or equal to. If we used greater than or equal to, an equal key would shift past its twin, and stability would break. Let's trace insertion sort on the array 5, 2, 9, 1, 5, and 6. We build a table like a teacher at the board. Each pass adds one new row and the old rows stay, so you can look up and see what moved. The top row is the start. The array is 5, 2, 9, 1, 5, 6. First pass I equals 1. The key is 2. 5 is greater than 2, so 5 shifts right and 2 drops into index 0. The amber cell is the 2 we just placed. The row now reads 2, 5, 9, 1, 5, 6. Second pass I equals 2. The key is 9. 5 is less than 9, so nothing shifts. 9 stays right where it is in the amber cell. The row is unchanged from the one above. Third pass I equals 3. The key is 1. 1 is smaller than everything before it, so 9, 5, and 2 all shift right and 1 lands at index 0, the amber cell. The row is now 1, 2, 5, 9, 5, 6. Fourth pass I equals 4. The key is 5. We shift the 9 right, then we stop. The next value to the left is the other 5. It is equal, not greater, so we do not shift past it. The key 5 lands at index 3, the amber cell, just after its twin. This is why insertion sort is stable. Last pass I equals 5. The key is 6. It shifts past the 9 only and lands at index 4, the amber cell. The array is now fully sorted, 1, 2, 5, 5, 6, 9. Predict, then reveal. One pass of insertion sort on the array 5, 2, 8, 1. Write down the array after I equals 1 finishes before you advance. Here is the answer. The key is at 1, which is 2. 5 is greater than 2, so 5 shifts right and 2 goes to index 0. The array is now 2, 5, 8, 1. The 8 and the 1 have not been touched yet. The C code maps 1 to 1 onto the pseudocode. The outer for loop runs I from 1 up to n. We copy A at index I into key, the next card to insert. We set J to I the while loop runs while J is greater than 0, and A at index J minus 1 is greater than the key. Inside, we copy A at index J minus 1 into A at index J, shifting it right, and then we decrease J by 1. When the loop stops, we write the key into A at index J, its sorted spot. Now the cost. In the best case insertion sort is big O of n, on input that is already sorted because the inner while loop never runs even once. That property has a name. It is adaptive. On average and in the worst case it is big O of n squared because reverse sorted input shifts everything on every pass. It is stable and it is in place with big O of one extra space. The full program is in the insertion sort file.